Digital AI really had it easy. It had the luxury of just gorging on the entire written internet. Trillions of words, right there just waiting to be swallowed up by large language models. But physical robots? Well, they're starving. Literally starving for high-quality data about the physical world. I mean, think about it. Teaching a machine to grasp a paper cup, feel its weight, and, not crush it into a million pieces? That requires a completely different kind of information. And sourcing that specific robotic data, it's incredibly difficult.
So to cure this data starvation, the entire industry is currently betting on exactly this number: 3. Yep, just 3 distinct data layers that companies are urgently utilizing right now to try and teach robots how to actually interact with our world. And together, these layers form what we call the Robotic Data Pyramid.
Okay, let's dive into this. Today's explainer covers the embodied AI data crisis. Then we'll climb the pyramid through Layer 1, real robot data, Layer 2, simulation data, Layer 3, human video, and finally, we'll look at flipping the data flywheel.
All right, starting with the embodied AI data crisis and the starvation for physical data. Like I mentioned, getting a robot to reliably operate in the chaotic, messy real world means you need data that goes way, way beyond text or static images. You absolutely need movement, you need physics, and you need intent. And the core problem keeping every robotics engineer up at night is that this highly specific physical data is just unbelievably hard to get your hands on.
Which brings us to the top of our pyramid. Layer 1, real robot data, the premium ground truth. This is the absolute apex, the gold standard for robotics today.
So what is this exactly? It's teleoperation. Picture this, human operators strapping into these wild VR rigs, looking like they're playing the world's most intense, futuristic video game, just to remotely control physical robots and perform everyday tasks. And while they do this, every single action is captured. The system is meticulously recording every sensor, every subtle joint movement, every camera feed. It's capturing the absolute core raw material needed for deployment because it's literally mapping human intuition directly into the robotic hardware. But the trade-off here is honestly pretty brutal. On the one hand, teleoperation gives you the most complete, authentic, ground truth information possible, right? It is the purest raw material for physical environments. But on the other hand, it is painfully slow and prohibitively expensive. You just can't scale it exponentially. You are constantly bottlenecked by the physical hardware you own, the literal square footage of your facility, and of course, the hard limits of human labor. And because this data is just so valuable but so insanely hard to scale, we are literally seeing the rise of data collection factories. Companies in China like Ajibot and Z1 are leveraging massive labor advantages to tackle this bottleneck head-on. Just imagine these massive warehouses packed wall-to-wall with human operators, basically waving their arms around all day just to manufacture this Layer 1 teleoperation data at an industrial scale. It's wild.
Moving right along to Layer 2, simulation data, the virtual training grounds. Stepping down one level of the pyramid, the goal completely shifts from premium human quality to infinite scalability.
This simulation data is generated by training AI inside advanced physics engines and virtual environments. And the brilliance of this approach, it allows robots to practice and fail without any of the physical bottlenecks of the real world. You don't need a giant warehouse, and you can safely generate millions of incredibly rare or even dangerous edge cases entirely in code. No more risking a multi-million-dollar prototype by accidentally dropping it down a flight of stairs.
And the undisputed heavyweight champion of this layer right now is NVIDIA. They're making massive bets on simulation, building out these highly complex virtual worlds for robots to learn in. And honestly, it's yielding some incredible results. I mean, we've already seen breakthroughs where robots are learning the insanely complex physics of ping pong entirely inside the matrix, perfectly mastering the game before ever even touching a physical real-world paddle. Now, what's really interesting about this slide is the fatal dual gap that's currently holding simulation back from being the ultimate silver bullet. First up, you have the sim-to-real gap. This happens when your highly trained virtual policies just completely break down the second they face the messy, unpredictable physics of the real world. Things slip, motors lag, you get the idea. And then, on the flip side, you have the real-to-sim gap. This is the immense, mind-bending engineering difficulty of trying to accurately model our chaotic reality into a pristine virtual engine in the first place.
Which brings us all the way down to the wide base of our pyramid. Layer 3, human video, the abundant foundation. This is the absolute lowest cost and most universally abundant raw material available to AI researchers today.
We are talking about tapping into the massive, endless ocean of internet and human-centric video. Because just by watching us on video, foundation models can actually build a sort of basic physical cognition. They sit there watching humans interact with objects, and they learn spatial reasoning. They learn how the physical world generally works, and crucially, they learn human intent. They essentially figure out what is supposed to happen in a given scenario.
But of course there's a catch. The pros here are pretty obvious. You get infinite scale at the absolute lowest possible cost, all while building up that crucial basic physical cognition. The cons, however, they're huge. Video completely lacks force, torque, and tactile feedback. Think of it this way. It's like trying to learn how to ride a bike just by watching the Tour de France on TV. Sure, you see what the riders are doing, but you have no actual idea how hard to pedal or how to balance your weight. The AI sees a human hand turn a doorknob, but it doesn't actually know how to move its own robotic joints to replicate that precise amount of friction and turning force.
Yet despite that massive hurdle, this right here is the absolute frontier. Silicon Valley heavyweights, we're talking physical intelligence, figure AI, Sunday robotics, they are aggressively pivoting to this exact layer. Their grand strategy is to combine reinforcement learning with massive pools of crowdsourced egocentric, meaning first-person, video collection. Basically, they want to bypass all that heavy, ridiculously expensive teleoperation of Layer 1 by squeezing every last drop of value out of Layer 3.
Just to give you an idea of how seriously the big tech giants are taking this, look at these specific projects: Apple's EgoDex and NVIDIA's EgoScale. Both of these initiatives are aggressively chasing the exact same goal: extracting high-signal, usable action data from mountains of low-cost human videos. I mean, think about the stakes here. If they can figure out how to translate a random YouTube cooking tutorial into precise motor torque for a robot arm, the entire industry shifts overnight. It would be a total game changer.
All right, let's bring it all together. Flipping the data flywheel, the secret to scaling. We have our 3 layers, and now we see how the machine really works.
So the crucial point we need to understand is perfectly captured in this quote right here. No winning model uses one layer alone. To actually solve the embodied AI data crisis, you absolutely need pure synthesis. You need the premium, high-fidelity ground truth of teleoperation. You need the massive, safe scale of simulation to handle the weird edge cases. And you need the basic, foundational physical cognition learned from endless hours of internet video.
But here is the secret to real scaling. It lies at the very base of the pyramid. Only that bottom layer, human video, can actually flip the data flywheel. Why? Because it is the only layer cheap enough and abundant enough to learn from continuous deployment loops. That messy, chaotic internet video isn't just some cheap fallback, it is the absolute engine driving the whole thing. Cracking the code on human video is exactly what will quietly power every single humanoid robot operating the layers above it.
And that, my friends, leaves us with the million-dollar question. Or, let's be real, the trillion-dollar question for the future of robotics. Who will crack consumer-scale structured human video first? Because whoever solves that final puzzle piece will completely unlock the full potential of embodied AI. Keep your eyes locked on this incredible race, because it is for sure going to shape the physical world around us, and much sooner than we think. Thanks for joining me on this explainer, and I'll catch you on the next one.